Thank you. So, good morning, everyone, and good afternoon and good evening to the people joining from other time zones. So, I mean, in India, it's evening, so good evening. Yeah. So, starting about today's meetup, right? So, we have today Neha. She will be the speaker today, talking about quantum computing and quantum cryptography. And this meetup is being organized in collaboration with Washington D.C., Toronto, and Indian communities. Uh, Okay, and so about Neha, she is pursuing her PhD in computer science engineering at the JP Institute of Technology, Delhi, India, and her area of research is quantum cryptography. And she has also completed a master's in which she worked on the polynomial time encryption with the QKD scheme, and her interest lies in quantum key distribution for secure communication. And she has also published several research papers sh- in connection to the emerging trends of quantum computing towards data security and key management and our computation methods. And she has also communicated her recent research work for the published. She was invited as a speaker for various talks in the field of quantum computing, and she's also working with different projects which are related to her interest, as well as she's closely working with environment-related projects apart from research work. So she spends most of her time in like nature, practicing yoga and meditation. That is something outside her work. And talking about the organizations who's organizing this kind of event, so we have Dave sir and Helen from Washington DC Quantum Computing Meetup Group. So Dave sir is based out of Washington DC, and Helen also I think she's based out of US. Correct me if I'm wrong, Helen. And I'm the moderator for today's session from Quantum Computing India community. Yeah. So that's it from my side. Without wasting time, I will hand over to Neha. Before Neha starts, if you have any questions or any feedback or anything you want to ask in between, you can either post your questions in the chat. I will try to answer as much as I can, or even Neha can take up those questions in the middle of the talk or at the end of the talk, whatever is convenient. Okay, and feel free to join the Washington DC Quantum Meetup group on Meetup and LinkedIn. This is the place where we announce most of our upcoming meetups and talks. If you will go and follow the Washington DC Meetup group, you will get to know about the upcoming events and upcoming speakers and topics, whatever we are going to organize in future. So yeah, over to you, Neha. I will stop sharing my screen and you can start. Anything else you have to add?
Can you talk about the upcoming events a little bit? The screens?
Sure, so let me share the screen then. It's visible, right? Can you see my screen?
Yes.
Yeah, all right. Let me just open the. If you go to meetup.com, right, and if you go to Washington DC Meetup, let me just open that. Let me search from. So this is the link where you will find the Meetup group page. You can just search for Washington Quantum Computing Meetup group, and you can see we have more than 2.5K members in the group. And this meetup is being handled by Dave sir and Helen. So if you see the list of upcoming events, so this is the one which is happening today. Next event is coming on 7th May, which is on healthcare and life sciences, how quantum is applied in these areas. For which the speaker, you can, when you will open the meetup, we can see that. And next meetup is coming on 21st May. That will be on exposing abstract mathematical structures to aspiring quantum pros. And similarly, we have an upcoming workshop as well, which is being organized for 2 days on May 25th and 26th. If you go and check the meetup, you will find the details there. For registration, you can see we have Eventbrite ticketing system where on this portal you can go and register yourself. And these are the list of the past events. You can see this community has organized approximately 90 events, and there are more going to upcoming in the future. So feel free to join this. I will paste this link in the chat. So if anyone has not joined the meetup group so far, they can directly join. Yeah, and do register yourself for the upcoming meetups as well, so that we can get the best out of these speakers. Yeah. Anything else, sir, you want me to add on to this?
Thank you.
Yeah. Okay. Thanks everyone for joining today's session. I will hand over the session to Neha now. You can please take it from here. Helen, we are recording the session, right?
Yes, this recording. This is recording.
Okay, all right.
Can we start?
Yes, please, Neha.
Yeah. So namaste, hello, good evening, good morning to all of you. I hope you all are doing good and you all are in high life state. So from the bottom of my heart, I would like to thank Washington, D.C., Toronto, and India Meetup for this wonderful opportunity. Today, I'm going to talk about quantum computing and quantum cryptography, whatever, little I know. So let us start. So very first, if I dig a little history about computers, then first generation started in 1939 to 1954. And that time we used to use vacuum tubes. In that particular time, as the basic component of memory and circuit for a CPU, we used to use this vacuum tubes. And at that particular time, installation and space required just to install and heat was, issue. If we move into the second generation, 1954 to 1959, that time we used to use transistor, and it was cheaper and it uses less power and it has more compact size than the first generation, and it is more reliable and faster. If I talk about third generation, it is also similar to the second one. Like we use, it in cheaper manner. It uses less power, more compact size, and it is more efficient and fast. Let us move to the fourth generation, which was in 1971 to 1991. And that time we used to use microprocessors. So thousands of this integrated chips are used on a silicon chip, and we were using that generation at that particular point of time. If I talk about fifth generation, it starts from 1991 until time. So it is still in development section, and more AI is used for the this software and for the computer thing. So let us talk about classical computer. And in classical computer, we have the number of transistors economically crammed into a single computer chip was doubling every 2 years. So it was a law which was given by Murray, and he told that, and he was a founder of this, co-founder of Intel, and he said that like every in 2 years, this silicon chip sizes going to increase, and now we are in a point of time where we have achieved this thing. Like we move to 7 nm to 5 nm, or maybe in near future we will move into the 3 nm chip size. But what is the issue in it? Like if I talk about the cooling and cost, so it is the major concern. That's why we all are moving into the quantum world. So we have some basic functions that we are using classical computers. So first one is accurate and speedy computation machines. Another one, it is our part of life, daily activities we are performing using this classical computer. So advantages of classical computer. So in any complex computation or any logic work like laboratory work, we can easily do on our classical computers, and many kind of numerical problems which are, which cannot be solved using conventional computers. So I will dig later a little bit. So conventional computer that are more focused on the classical principles, like electrical network are either on or off. So at particular point of time, only one operation is going to perform. For example, if I talk about factorization of a number, so like the computer time required to factor an integer containing n digits is believed to increase exponentially with the time. So let us talk about quantum. So how this quantum word arrived. So what does quantum mean? The word in quantum computer originates from the quantum mechanics. So as classical computer works on the mathematical things, so quantum is going to work on the quantum mechanics principles. So a basic theory in physics, which is coming from the quantum mechanics. In brief, on the scale of atom and molecule, matter behave in a quantum manner. That's why we are using this quantum. And what is quantum computer? A quantum computer is a machine that performs calculations based on the law of quantum mechanics, as I told, which is behavior of particle at the subatomic level. So if I talk about the history of how this quantum computer came into the picture. So in 1918, Max Planck gave a theory of energy quantum. So Max Planck was known for the originator of the quantum theory of energy. And he told that energy of light is proportional to the frequency. After that, Einstein came into the picture and he did discovery of the photon, and he told, like, he created a quantum theory of light, the idea that light exists as tiny packets or particles, and it is called, and Einstein called those particles as a photon. Then we have in 1980, this idea of quantum computation came, and it is an area of computing which is focused on developing computer technology based on the principle of quantum theory. So it explains the behavior of energy and material on the atomic and subatomic level. So in 1996, this Grover came with an algorithm which we are, using just to solve many problems. So it is this algorithm was used to solve this unsorted database problem. So we have three pictures of quantum mechanics. One is Schrödinger, then Heisenberg, and third one is Dirac. So if I talk about Schrödinger, so it is an equation which is used to find the allowed level of quantum mechanical system, such as atoms or transistors. So he told that the wave function gave the possibility of finding the particles at certain level. Then Heisenberg's come into the picture, and he told we cannot know both the position and speed of a particle, such as photon, electron, with a perfect accuracy. We cannot measure position as well as momentum of a particle with absolute precision. Then Dirac, he told that the two systems interact with each other for a certain period of time and are then separated. They cannot longer be defined as two distinct systems, but become a single system later. So classical computer versus quantum computer. If I talk about classical bit, so it uses 0 and 1. And if I talk about quantum, it takes a 0, 1 superposed state of 0 and 1. Means if classical bit, if we are applying n bits, then we are getting result as a n bit also. But if I apply n qubits, I'm getting 2 raised to power n solutions. So it is doing, parallel processing also. That's why it is not bit, but it is fast. So classical computer versus quantum computer. A classical computer, as I told, it uses binary bits, which are 0 and 1. We can copy those bits also. And if data, so it will take is equal, it should be equal to 3 bits, means 3 bit equal to 1 data value. If I talk about qubit and quantum bit, is not taking 0 and 1, but it is taking in a vector form like magnitude, adversarial direction, and it follows one principle, that is no cloning, and it is not possible to copy the states. So if data is equal to 3 bits, then 3 qubits will give you a data value. How? That I told, it will give us 2 raised to power n solutions. So a qubit or quantum bit is the quantum analog of a classical bit, in which information is encoded in a bits where each bit take the value 0 or 1. So in quantum computing, the information is encoded in qubits. So a single qubit represent into 2-level system, which is linear combination of states denoted by 0 and 1. These states are denoted ket 0 and ket 1, which is 0 state will give 1 0 and 1 state will give 0 1, and 2 possibilities. A pure qubit state is represented by psi is equal to alpha 0 plus beta 1, where alpha and beta are 2 probability amplitudes, which in general are complex number, which is in the form of a plus iota b. So if I talk about quantum gates, so quantum gates transform qubit just like classical bit do, and they are changed by the classical gates. However, what is the main difference? If I talk about classical gates, so we are not getting output like we got in quantum gates. So quantum gate gives us a reversible thing. So one such example of a single qubit gate is the quantum NOT gate, that changes. If you apply 0, it will give you 1, and if you apply 1, it will give you 0 state. So the corresponding unitary matrix will become x is equal to 0 1 1 0. So the other example is Z gate. This change 0 to 1 and 1 to -1. Next, if I talk about again quantum computers, so if I am giving 0, it is giving me two output 1 0, and if I am applying 1, I'm getting 0 and 1. So this I already discussed, psi alpha 0 plus beta 1. So the main thing that I wanted to share here is one qubit needs 4 real number, and one real number lie between 64 bits. So one qubit is equal to 64 into 4 bits, which is actually bit difficult to simulate on a system. So the symbol bra and ket tell us a row vector and a column vector. So column vector representation is ket, and row vector presentation we use bra, and we tell this as bracket notation. So if I talk about Hadamard gate, so if I apply Hadamard gate to a qubit that is in state 0, it brings the qubit in a superposition state, where the possibility of measuring 0 is equal to the probability of measuring 1. So if I talk about CNOT gate, then this gate is a conditional gate that perform on X gate on the second qubit, which is target. If the state of the first qubit control, then it will give us this ket 1. Then these are the most important gates just to perform any algorithm. And another one is entangled gate. So two members of a pair exist into a single qubit state. If I change the state of one qubit, it will spontaneously change the state of the other one. What it means? And then the other one in a predictable way, means we can predict if we measure one state, then another one we can predict. So these are the areas where actually work is happening. So circuit model or gate model, as if I talk about classical computer where we use gates, same way we are using circuit model or gate model just to perform some operation. You can see the right side. Another one is adiabatic quantum computing. Directly we are not using these computing because we need maintain some specific levels just to use these state, and they are used for certain, or you can say specific problems. First, we just have to maintain that level. After that, only we can use these things. Next is quantum annealing. It is quite similar to adiabatic quantum computing, because in this we just have to, maintain one universal state, or you can say maintain a higher level. After that, we can use it. Next one is topological quantum computing. Yes, so we have topology also, and in which we have a collective particle formed from a fundamental particles like atom, you can say electrons or photons. From fundamental level, we are just getting collective particles. So we have also physical realization of quantum computers like superconducting, quantum dots, linear opticals, trapped ion, color center, so and so. But we have few challenges also. Like first one is decoherence, noise, scalability, quantum error correction. If one wants to create any ripple effect, so that very first time we just have to maintain the first state, so that we can maintain another ripples. But we are getting challenge here, because we have so much noise in our environment. So we were unable to, and we are unable to maintain that state. You can say environmental noise like rainy days, snow days, or any other noise. And if we talk about scalability, so number of operations you apply, that is when you want to maintain or observe that state that is not happening as of now. So, and if I talk about quantum error correction, so it is also like cloning quantum state is impossible. I'll talk about on that also. If I talk about quantum technologies, then we uses separate individual quantum objects like molecules, atoms, electrons, and photons. So most important quantum effects are, as we know, that is superposition, entanglement, and interference. So we have few other quantum effects, which are no cloning, tunneling, uncertainty principle, and teleportation. So we have fundamental concept of quantum computing. First one is uncertainty principle. They can't know everything about the state of the quantum object. And in superposition, if qubit state can be 0 or 1, also can be represented as a linear combination of states. Entanglement is a state of a composite system that cannot be written as a product of state of its component system. And interference is something which controls the probability of a system of qubit collapses into a particular measurement state. It is a byproduct of superposition and allows us to bias the measurement of a qubit towards a desired state or set of states. Then we have few quantum effects. These effects are teleportation, no cloning, observer effect, and tunneling effect. So data transfer possible from one qubit to another, separated by a distance, when we could extend the entanglement between the across this distance, or you can use Ipier-Bell states. So no cloning theorem says that no way to copy one quantum state into another. This no cloning theorem, maybe I'll cover later also. Another one is observer effect. So if someone wants to measurement of quantum state that cannot be made without affecting the system, that is without changing something in a system. And if you talk about a tunneling effect, or you can consider it this tunneling effect as a barrier, some physical barrier in the system. So quantum tunneling or tunneling is a quantum mechanical phenomena where a subatomic particle's probability disappear from one side of a potential barrier and appear on the other side. So particle is able to penetrate through a potential energy barrier that is a higher in energy than a particle of kinetic energy. So let us talk about quantum cryptography. So quantum is a Latin word which means the smallest possible and discrete unit of any physical property such as energy or matter. And cryptography is a Greek word which means secret writing. So it is an art and science for achieving by encoding the readable format into data into a non-readable format. Next, cryptography. So we have cryptology, in which we have cryptography, cryptanalysis, and stenography. So we have a plain text. We need to encrypt that text using ciphertext, and we will decrypt, and we will get the plain text. This is our cryptography. So we have few methods how to achieve that cryptography. So we have two methods. One is symmetric, another one is asymmetric. If I talk about symmetric, then we have to use same key for the encryption as well as decryption. If I talk about asymmetric, we just have to need key pairs for encryption and decryption, which are public and the private. So symmetric key algorithm, we have a plain text, we do encryption using a key, then we'll convert it into a ciphertext, we'll do decryption using the same key, and we will get the original plain text. It is also called a secret key cryptography, in which we are just using single symmetric key for both encryption and decryption, and this key must be known to both the parties, that are sender and receiver. If I talk about asymmetric algo, so in this kind of algorithms, we need two keys. As you can see, we have plain text, and I am doing encryption using the public key. Then I am getting one ciphertext. Again, in this ciphertext, we are applying private key just to decode it, and we are getting the original plain text. So private key are used for the decryption, and public key is used for the encryption. If I talk about classical algorithms, the pioneering development is happened in this field in 1970s. And we have this Diffie-Hellman key exchange, RSA, public key crypto system, elliptic curve cryptography, and Diffie-Hellman key exchange, which is based on the discrete log problems. We have RSA, and we have the security would be compromised in post-quantum era. That is why we are moving into the quantum world. So what is the solution? We have lattice-based and code-based crypto system. And in this NIST research, I have included one reference where they announced the solution for this thing. And it is maybe used shortly in commercial domain in case quantum computers arrive. And if I talk about any alternate solution, so alternate solution is quantum cryptography. It provides security against quantum adversary without unbounded power of computation. So we have classical computer, and we say our message, whatever message is we are doing, that is secure. But there are chances, and it is happening, and it is recorded on national and international level also, like our systems are not secure. So we have to meet with some accidents, like attackers easily hack our data. So like brute force attack, chosen ciphertext, and attack and frequency analysis. So hackers tries all the possibilities. So how can they break security? So whatever possible values they can get from the plain text, or maybe from they just try to break the key. And for that we have quantum cryptography. So quantum cryptography is a cryptography of 21st century, where we are using quantum mechanics, or you can say laws of physics. Based on those laws, our message is secure, or you can say our information is secure. So an important new feature of quantum cryptography is that security of a quantum cryptography protocol is based on the law of nature. As I told, it is based on the quantum physics and not on the unproven assumption of the computational complexity. Like quantum cryptography is the first area of information processing and communication in which quantum particle physics laws are directly exploited to bring an essential advantages in information processing, so that we can make our communication very much secure. So, but security in quantum cryptography is unbreakable because it is following the laws of physics. We have two major areas in quantum cryptography. One is quantum key exchange. So we are exchanging bits securely via a quantum channel with the help of classical channel, which can be public, but it should be authentic. Another one is cryptography on quantum computer, which is based on the Shor algorithm. So we have few outcomes so far. So it has been shown that we have a quantum computer, we could design absolutely secure quantum generation of shared and secret random classical keys. It has been proven that even without quantum computer, unconditional secure quantum generation of classical secret and shared key is possible, in the sense that any eavesdropping is detachable, and we are working on post-quantum cryptography also. So unconditionally secure basic quantum cryptographic primitives such as a bit commitment and obelisk transformation are impossible. So quantum zero knowledge proof exists for all NP complete languages, and quantum teleportation, which I already discussed, and pseudo telepathy are possible. So quantum cryptography and quantum networks are already in advanced experimental stage, and this is the basic idea what we do in quantum cryptography. Like we have a Alice sender and we have a Bob receiver, and Eve is a eavesdropper who is trying to hack the whatever communication is happening between the Alice and Bob. As I discussed, we need a public channel. It should be it can be a telephone or internet, but we need a quantum channel. Through that we are achieving security. So basic idea is in early 1970s, a paper came into a picture which was on the conjugate coding, and this paper was later came for the base of the BB84, which was invented in 84. So most of the work on QKD is happening only on this. Then prototype is developed in 1991, and QKD protocol was invented independently in 1991. Then, so we call better name of this quantum cryptography is quantum key distribution. It is not a new crypto algorithm. So two physically separated parties can create and share random secret keys, allow them to verify that the key has not been intercepted by anyone. So why we are moving into the quantum world, though we have all the things with us. So the main idea behind it is like NIST crypto standards, they are launched, and they told that we have algorithm as of now which are working on the classical computers, and we can, if I say like we have algorithm and we have information also, so we can provide security for that particular information for next 20 years. So I just have to make my algorithm very much mathematically or computationally very much secure till the time quantum computers not come into the reality. So cloning possible in a classical domain, but not in a quantum. You can see through this picture, we have a possible to copy a classical bit, but as you are trying to, clone a quantum bit, it will disappear. So I would like to give one example here. So imagine yourself, you are in a dark room, and from a hole, sunlight is coming to you. So just focus on this. Like if you try to catch that light from a particular hole, so that light will disappear. That is a simple example which tell us like cloning is not possible. Whenever you try to clone, it will disappear. That state will disappear. So as a result of quantum mechanics, it is not possible to create identical copies of an arbitrary unknown quantum state. And it was stated in 1982, and these are the papers from where this information is I have taken. So let us consider a scenario. First, you can see key is a stream of photons or light, and photons has a property called spin, and we have 4 filters how this spin is moving or passing through these filters. So first, photons are coming. Second, photons have property called spin. And third, we have 4 filters. And now we have 2 schemes. One is diagonal schemes. Another one is rectilinear scheme. In diagonal scheme, you can say we have horizontal and vertical bases. These are 4 bases. And in rectilinear also we have bases, 4 bases. So we have 2 scheme. Like if I say this is vertical one and 45 at 45 degree one, and this is horizontal 0, and this is minus 45. You can see this state same here. Now, if in classical bit we put a ball in a classical box, the color of that ball that pop out is the same as the color we put in. But if you talk about the quantum bits, if we put the ball in a quantum box and open the wrong door, the color of it is a probability. The color of the ball that comes out is random. So it is based on the elements of the quantum physics. Like we have unpolarized light, and it crosses through a polarizer, and then it become a polarized light. Now polarized light through the polarizer. So if you say if you see this incident wave is coming, and it is going through the polarizer, and it is transmitted. Next, you can say here is incident wave, here is a polarizer. This incident wave is going through a polarizer and reflecting back. Another one, you can see this is a incident wave which is coming, and half of the wave is transmitted and half of the wave is reflected. So here, this you can see horizontal polarization. In second, when this wave is reflected, we call it vertical polarization. And when 50% of the wave is transmitted and 50% of the wave is reflected, we call it arbitrary linear polarization. So no light can pass through orthogonal polarizer, and it is same for photon. You can see we have an incident arbitrary light, so it is reflected and reflected horizontally and vertically, but it cannot transmitted. So polarization state of a photon, like a photon, if it is a vertically polarized and if it is a horizontally polarized, a photon on 45-degree polarization and a photon on minus 45-degree polarization, then we have a concept of quantum indeterminism. So a physical state such as a photon exists partially in all its particular. You can see through this vertical filter and vertical filter. You can see we have a vertically polarized photon here, and we put our filter in a vertical direction. Then you can see 100% of this polarized photon is passing through this vertical filter. And if I talk about a horizontal polarized photon, if I place this photon in a horizontal manner, then and I'm using vertical filter, then the zero passing rate means it is this vertical polarizer is blocking this horizontal polarized photon. So if I talk about this state, a photon in neither in 45-degree or minus 45-degree state, then what is happening? If we try with this state, then the result will go random. We cannot predict that result. So we have 2 important properties. One, in order to correctly identify the status of a photon, the basic must be known quantum indeterminism. And next one is measuring a photon destroy its stain, thus no cloning. It I already proved with this example also. So let us talk about BB84 protocol. In this, we using this quantum cryptography, and it was discovered in 84. That's why we call it 84 protocol. So here you can see we have a light source. We have 4 filters here, 0, 1, 0, 1, minus 45, plus 45, then horizontal and vertical. When Alice tried to, send these bits from here, and Bob is measuring states, then what we are getting? We are getting then we are getting a state where Bob bases are this, and whatever bases are matching, they are collecting those, and at a particular point of time, they are just measuring with each other, like they got same bit or not. If they got same, it means their whatever communication they are doing is secure. If they are not getting those, means whatever they want to just wait a second, whatever they want to tell each other, that is intercepted by the eavesdropper. So let us talk about this. All present day computers, whatever classical computer we are using, uses binary 0 and 1 logic, and all computational follow yes or no answer. But Feynman in 1982, he suggested that it might be possible to simulate the evolution of quantum system efficiently using a quantum simulator. So what is special about this quantum state? We have coherent superposition, we have entanglement. These both I already completed. So if I talk about classical things, we have 0, 1, and if I talk about qubit thing, we have a bracket 0 and bracket 1. We have this, I think I already covered. Let us talk about quantum algorithms. So these algorithms, first we have factorization, searching, sorted, and distinguish constant and balanced functions, and quantum algorithm for the linear system of the equations. So these algorithm, like classically you can see it is taking up to the 400 digits, and it is taking 10 raised to power 10 year. It is the age of universe. And sure, given another algorithm which is working with the polynomial times. If I talk about another quantum algorithm or quantum computer, then we have 6 into the picture, like trapped ion, polarized photon, QED, quantum dots. Just wait a second. Cold atoms and NMR. So if I talk about trapped ions, so its focus is that, so electromagnetic waves that are holding ions in such a way so that it minimizes the environmental noise and decoherence. And this polarized photon I already shared. If I talk about cavity quantum electrodynamics, then quantum field theory of the interaction of charged particle with the theory of interaction, like it is also working with the electromagnetic field. If I talk about quantum dots, then a semiconductor or nanoparticles which exhibit size and composition depend upon all the optical electronics property that we have. If I talk about cold atoms, then again quantum bits of information, many atoms arranged in a space could build a quantum register. So it is working on one by one. And last one is NMR. These are a nuclear magnetic resonance, and it is mainly working with the medical images, you can say. Then we have a list of few top quantum computing companies, which is ID, Q Quantine, Qcrypt, Single Quantum, Post Quantum, Crypto, QuantIQ, and Crypto Next Security. Then we have a QKD commercial product also. I have attached 2 links in it. So this was one example which I found very much interesting, like quantum computing exemplary use cases. So the aspect of quantum computing can very well be applicable to autonomous vehicle of the near future, where these vehicles can be guided to a particular area of focus, or it can also intimated to avoid that area together, particularly in a heavy traffic solution. For example, you can see this in this area, we have a cab in a location 1. If I talk about classical computing, you can say it calculates the number of customers who require a cab in a location B versus number of empty cabs that are available in location 1. So So in quantum computing, we process the data and directly empty cabs from location A to location B, which is equal to the cabs for all expecting customer which actually need it, and they are getting the solution of this problem like this way. Then if I talk about experimental cryptography, so we got success yet also. So we were able to transmit using optical fibers to the distance of 120 kilometer, and open air transmission to the distance of 144 kilometer at daytime from one peak of Canary Island to another. Next goal is to Earth to satellite transmission. So all current system use optical mean of quantum state transmission. And if I talk about the experiment and the problem we have got after that, those are no single photon source are available. So weak laser pulse currently used contain in average 0.1 to 0.2 photons, and loss of signal in the fiber is happening, and it is also providing us error rate. Then to move from experimental to development stage, these we are doing. Now, if I talk about quantum supremacy, then we have three algorithms. First one is Simon, then Grover came, and then Shor's algorithm used for the factorization purpose. If I talk about Google supremacy, so the paper published in Nature on 23rd October 2019, and they claim that the Google has achieved supremacy with their 53 qubit quantum processor, and right now we are more than this number. So they claimed at that time in the task of sampling the output of a pseudo random circuit, they found some of bit strings are much more likely to occur than over in 200 seconds. But classically computing, this probability distribution become exponentially more difficult with the number of qubit and the number of gate cycles. But if I talk about this classical computer for the circuit, which have been demonstrated in 10,000 years. However, IBM challenges their claim, and they found that using some clever strategy, the problem can be solved in 2.5 days in supercomputers. And then we'll talk little about this machine learning. So some tasks that are hard, if not possible to be programmed into a computer, for example, how to distinguish a cat from a dog. So instead, we let the computer or our machine to perform some trainings. So we are getting this picture. So if we are applying cat, we are providing picture of cat and dog, and then as output, we are getting cat and got it. So if I apply machine learning on it, then what is the holdup with classical machine learning and SVMs? Why do we even need to add quantum computer, though our tasks are already performing using classical computers? So in quantum machine learning, when data points are projected in higher and higher dimension, it is very much hard for classical computer to deal with such large computation. As I already mentioned one example, if we try to simulate 64 into 4 qubits, so it would be a great task for ourselves, like our machine will not support this. So even the classical computer can handle it, it would take too much of time. So simply we put some time on classical machine learning algorithms that are too taxing for the classical computers. Luckily, quantum computers have the computational power to handle these taxing algorithms. They utilize powerful laws like superposition and entanglement to solve problems faster than their classical counterparts. That's why maximum people are moving into the quantum machine learning just to solve these NP hard problems. So let us talk about quantum machine learning and QML. So you can say classical machine learning, CML, we have a classical data like 1 and 0 in the form of bits. We are applying many mathematical algorithms using CPU and GPU, and we are able to recognize the pattern. Here the main thing you can check is a time. So in quantum machine learning, if we are applying quantum data like qubits, as I already mentioned, this quantum qubits are doing parallel processing. So we just not need to go, step by step. But what is happening, like this quantum data qubit is doing superposition of states, then it is also applying mathematical algorithm, then it is doing, here CPU is doing processing, here quantum processor is doing processing, and we are able to recognition patterns in a few seconds. What is the processing method for it? Like if we are taking n bits and we applying this using the CML, and we are generating some output. But same thing if we are happening using qubits, we are generating first of all 2 raised to power n states. So it is doing, the parallel processing and provides the fast results. So in fact, a study of IBM and MIT found that the SVMs are mathematically very similar to what goes on inside the quantum computer. So this was the one project in which we are utilizing SVMs for the classical of this Parkinson disease. So a QML algorithm to identify whether a patient has this disease based on their speech feature. So it was conducted using a 9 qubit simulation on a IBM quantum simulator utilizing a quantum support vector machine. And so the application was, the first step is to set up a circuit, then import the necessary packages that we need. Then we just have to load our IBM account credentials and connect to the optimal quantum simulators. After that, we need to set up a number of shoots that we are going to attempt, or our algorithm will take care of that. At the next step, we just have to prepare our data set. So import your data set, whatever data set you want to take, and split that data into the 2 classes, that is present and not present. Then divide the data into a training and testing. The ratio should be 7:3 training and for the testing purpose. Then we need to build a quantum algorithm. So for that, set up the number of qubits the circuit will have, or you want to apply. Then the number of qubits should be equivalent to the number of feature in your data set. Whatever feature you want to extract, you have to apply equivalent qubits in that, and you have to initialize the feature map to build the SVM. Then set the necessary parameters, like including the device it will run on and number of shoots, and initializing the pseudo number generator. After that, import unlabeled data for the classification that we left already. Then the last step is to run the algorithm, and the run method will generate the accuracy of the circuit. Meanwhile, the predict method will do training, testing, and prediction of the unlabeled data. So prediction of the disease based on the speech indicator accuracy is 0.75, and prediction from input data where 0 is equal to healthy and 1 is equal to present, as I already mentioned. And what would be the result? The result shown can predict whether or not each of 9 patients have disease with 0.75 accuracy rate. With a larger data set and more stable hardware, the accuracy rate will only go up. If you will use more number of rounds, or you will apply more qubits, then it will always give you high accuracy. So with this disease, the earlier the detection, the better the treatment. So this way we can solve many health related problems also. And QML algorithm like this one will be able to make huge strides in treatment and disease prevention. Like we have so many problems, and people are also working on this DNA protein folding, and on many drugs. You can say it is, if we are into the practical realization of this quantum computer, then we can make a huge change in a medical field. So in the coming year, QML is going to become a massive field with increasingly more computational power, and it will have the capacity to solve the world's most complex problem. The AI revolution of today will be even bigger when combined with the quantum computing. So this is the link of this disease that is predicted with 0.75 accuracy. So we have a basic linear subroutine, and on that we will do the comparison. So if you see, like, QRAM is quantum random access memory, whereas you have a fast Fourier transformation, its complexity, finding eigenvector and eigenvalues, its complexity, and like it, whatever solution you are going to provide, you just have to run all the things using QRAM. And we have some key points here. These quantum subroutine will dramatically reduce the computing power of the majority of self-learning algorithm, which we are training under our machines. The key point here for this kind of quantum algorithm used in machine learning is to show how you can take a large classical vector of data and to map it in quantum state. As I told, we can take a larger and larger data set, as it is going to give result within seconds, because it is working on the laws of physics and doing parallel processing for this. And for this, you need a device that is going to take classical data defined, for instance, in a mirror of compact disk, or classical data defined in pulses of light that are going down to a fiber optic cables, or classical data that's stored in a capacitor in an integrated chips that integrated circuits that I already discussed. And you have to be able to map into a quantum state, and the device that will do this for you is called quantum random access memory. So you can see here quantum speedup in machine learning. So in this table, speedups are taken with respect to their classical counterparts, and which mean this quadratic setup and exponentially relative to the classical counterparts. And the conclusion is, like, quantum mechanics is weird, and quantum system can generate weird patterns that are very hard to generate classically. But quantum state can also learn and recognize weird patterns that cannot be recognized classically. And the reason that they can do this is that quantum computing and quantum mechanics is all about this linear algebra. Using that, we are only able to find out the solutions and algorithm, and able to design and develop the algorithms. But with a very small number of quantum bits, we can have state that represent vector in a very high dimensional vector space. And then quantum computer can be used to do linear algebra operations, such as fast Fourier transformation, finding eigenvalues, eigenvectors, and inverting matrix exponentially faster than we can do classically. So at last, we have current cybersecurity. Best practice call for multiple security layers, and I expect that will remain true even as we perfect quantum technology. While the capabilities that quantum cryptography offer are powerful, a hybrid solution will likely be the best approach. And in short term, post-quantum cryptography looks more promising as a widely deployed solution till the time we don't have this quantum computer practically in a implementation thing. This was all from my side that I wanted to discuss.
Thanks a lot, Neha. Yes, I can hear you. Thanks a lot, Neha, for this amazing presentation, and it was very insightful for each one of us. Hope
Thank you.
For learners as well, they would have got a good amount of learning from your session. So we have a few questions in the chat. I will just read out, and it's good if you can answer them, okay?
Yeah, sure.
Sure. Let me start with the first one. So, and participants as well, if you want to, you can just raise your hand and you can unmute yourself and ask the question. So yeah, we have a question from Dr. Kumar. Where it is? Just let me go through this.
Can I ask meanwhile?
Yeah, you can ask it. Yes.
Okay, so I put in the chat, I asked to explain the no cloning,
Yeah.
which is kind of a, in my mind, limitation of the quantum approach. And the reason is, first of all, no cloning, as I put it in the chat, you already explained it a little bit by saying no copying. But no copying is very limiting in the sense that there are many mathematical proofs and techniques that use exactly copying.
Yep.
Because if I have copies of my objects, I can manipulate them better. So maybe this is a niche to explore.
Yeah, I'm so sorry for that, but I'm clear about that. We cannot make, I think, identical copies for particular thing. I hope I'm right.
So I don't follow. You say that I have to adhere to this restriction? I mean, nobody tried to copy a quantum state experimentally?
So it is impossible to create an independent and identical copy of an arbitrary, whatever unknown quantum state we have. So state must not be known.
So Neha, let me come to your aid here. Basically, the particle is in constant state of motion. That's why we have these, all these, when you take all the state versus 0 and 1 is absolutely binary, whereas this becomes what you say in the constant state of wave and motion. Wave, it's a wave, it's a particle, it's a dual state. And that's why we have these qubits needed to represent it. And that's the reason cloning from that angle is not possible.
You mean I cannot copy ambiguity?
Exactly.
Okay, got it.
However, statistically, if I take many, many ambiguous states, I can average them.
That's
and it's
true.
done
That's
in
right.
statistics so many times.
That is correct. You
And
can
it's a
average
beautiful
them.
trick, actually.
Yeah.
So why can't we use this trick here?
Yeah.
Yes,
That's
sir,
why
got it.
exact copy is 0 and 1. That's why we say it's binary. In the quantum, it is not binary.
Yes.
Actually, I have one point. So is it because of that phase factor value, it's not possible to copy because phase factor value can be infinite number of possibilities? Is that the reason, or I'm missing something?
Your question has the answer in it, and you answered it. So Mendel.
Yeah, is it? No, I'm just trying to clarify. Is it because of that?
All these are a lot of ambiguous factors in quantum mechanics. That's why we still say there are still a lot of unknowns, and yet we are trying to leverage this technology and possibility. That's where we are headed. Yeah.
Okay.
Okay. Somendu, I gave the answer for your question as well. You were asking about
Yeah,
QKD, if it is unbreakable. If you're not satisfied with the answer, you can ask Neha.
Actually, it was not fully clear. So yeah, if you can elaborate a little bit, that will be great. Okay. Because I'm not from quantum computing.
Neha, would you like to take? Okay, no worries. Neha, would you like to take Somendu questions? He was asking about is QKD really breakable? If yes, then it is because of the quantum phase factor.
Actually, I'm not getting the question. Can you please repeat it?
Sure. So Somendu's question was like we have QKD, right? Quantum key distribution.
Yes.
Yes. So his question was are these QKD really breakable Unbreakable.
Yes.
I mean, why quantum key is not breakable, and is it due to quantum phase factor?
Okay, so I would like to elaborate this using one example. So like we have this BBH4 protocol, as you told, like how QKD is not unbreakable. Like whatever I am able to understand is like it is working on the laws of physics. One point. And second point is, as I told with that example, if you really want to, catch any state of a photon or a light particle, it is going to, distract, or no one can catch that particular state. So this is one reason. If like we are doing it in communication, one side is sender, another side is receiver,
Because of uncertainty principle, you mean?
yes.
Okay.
And we have 3-4 factors also, like this entanglement and superposition states, because we have photon, but I can
I
also
haven't still completely changed my plans, period. Meaning I can brush my teeth and get out of the house.
You can continue. Yeah, I mute the participant.
So I want to explain using it example also, like I told in the time of presentation also, like see, if you really want to catch the photon state, then photons has some fundamental properties like spin, so and so, that I elaborated in the presentation also. If you consider this like if you have a light particle and you want to catch that light particle, that is going to disappear, because you cannot catch light particles same way. Maybe whatever I am able to understand, like QKD is unbreakable because it follows few principles of quantum mechanics, which are, nature has hide something from us. Like you can consider it as uncertainty principle also, and entanglement and superposition state also. And if someone wants to add anything in it, please go ahead.
I will
thanks,
just
Neha.
add a couple of comments. Sorry, go ahead, Sumendra.
Yeah. No, I just said thanks, Neha. Yeah, that's all.
Yeah, no, I'll just add something it's a very interesting example which has allowed me to kind of comprehend and yet uncomprehend the quantum situation. And as we are saying, there are some unknowns still. If I give you a pair of socks and it is not labeled right or left, how do you identify which one is right, which one is left? That is a very classical example to understand this kind of situation. And as your photon, and you took that example, when it comes to classical computers, we say cat and dog, and we do the feature extraction, and then we identify whether it's a cat or dog. Now, come to the other side of the story. And that's why I took that example of socks. Right or left, you put the right and left, left and right, unless it is labeled and you want to go specifically with the label, you'll never be able to say, yes, this is going to be my right foot sock, or this is going to be left foot socks, right? So that's where that multi-positioning is there in this situation, which we call as superposition. And that's why, and you gave a beautiful example, Neha, in your presentation, where you showed exactly we cannot capture the light. And then there were various depictions of that. So that basically continue to build that uncertainty which we have around which, and that's why we always try to estimate, and we use all the probabilities and all the algebra to get and finally arrive at the results, rather than being 0 and 1 possibility. And even if we go for machine learning examples, in the end, we always say 0.75, 0.9. We continue to increase that surety. Are we 100% sure? Those are very minimal situations, right? That's why we continue to evolve our engines. That's where it is. Thanks.
Thanks, Green sir and Neha, for answering the main two questions. Yeah. Next, we have from Ilfiltron Software Suit asking about, do we have any other boot camps? Yes, we have like many such programs happening across the globe. So you can follow a few of the websites like Quantum, even communities like Quantum Entangled, Q World, if you have not heard of, then QCI, Quantum Computing India from India. And there's one website I will mail you. I'm not able to recall the name right now, where they list all the meetups and upcoming events as well. And even universities are coming forward to host these kind of boot camps and events for students and professionals so that they can scale up in the domain of quantum computing. Okay, so maybe we can connect offline and I can share you all the resources with you so that you can attend such events. Next, we have, okay, we have one question from Kianush asking, can we break the RSA cryptography by Shor's algorithm? Neha, your comments on it?
Can you please repeat it? I'm so sorry. The voice is breaking.
Okay, can we break the RSA cryptography by Shor's algorithm?
Yes, there is a very beautiful mathematics behind it. And if you try with algorithms also, you can prove it. Maybe I can also give, but I think I don't have proper setup now.
Sure. Kanish, I hope this was helpful. Anyone else having any other questions, please feel free to unmute yourself and ask. We are trying to make it more interactive, and if you have anything related to the content, what Neha has presented, you can ask those, or if you have anything from the learning side or from the community side, or how you can get started, or how you can be part of any of the communities, you can ask such kind of questions as well.
Anirban here. Am I audible?
Yes.
Yeah. So basically, my question is using the concept of quantum computing, where there are more than two states compared to bits 0 and 1. Theoretically, is it possible to reach the nearest exoplanet at the speed of light? Because normally using classical computing, it might take 75. I'm not sure. 75 years or 75 thousands of years. So. Is it possible to reach the speed of light with using quantum computing? That's my question.
That's very interesting angle of it, what you're trying to look at, Neha. I don't have idea about this. So Neha or
I think I'm not right person also to comment on this. If someone is from physics background or any professor here who wants to comment on it, please enlighten us with the answer.
Viren sir, anyone?
So you mean you want to cross the limit of
No. I don't want to cross it, Somendu. I think it's impossible to cross the speed of light. But
according to Einstein.
Yes. Yeah, but quantum laws are breaking the actual all the laws which are there in physics. That's what I see. But what I understand is we can travel at the speed of light if we are not, because
you cannot achieve speed of light unless you are massless. That is in case of photon.
Yes. Exactly. So with the mass, it is going to. But is there any research done on that? I just wanted to check.
Actually, I'm not sure. I am not a black hole physicist, but in case of black hole, every laws of physics breaks down. So maybe it is possible. It's my guess. Don't take it seriously. So it may be possible because lots of laws of physics breaks down there. So in that case, it may possible. But in quantum mechanics, it's not. You cannot cross that speed of light.
No, I'm not trying to cross the speed of light.
No. I'm just saying.
At least achieve.
Yeah. No. I think once CERN published some paper. I think I saw in the in newspaper when I was in India. So they crossed the speed of light, but with a huge error bar, which doesn't make any sense. So
So there is no mass involved. That is like just a transmission kind of is what you're
No,
saying.
I cannot remember how or what was the context, but it was very surprising how they mentioned that. But when they run LHC, it's they are when they collide with proton and proton, I think it's around 99% percent of speed of light,
Yes.
but
Yes.
it's not 100% because
Yeah.
proton have some mass, some 9
Yeah.
and
Right.
938 or something MeV.
Right.
So yeah, it's not.
Right. Means theoretically, what you say is, if we consider photons, which are the
Massless.
basic constituents of quantum physics, we can think like up to 99% can be achieved if it is massless. So if we don't have any mass of the thing, so that is like theoretically possible. That's what you're saying.
Yeah, if you look at the mass formula, moving mass, as per I can remember, m is equal to m0 by root under 1 minus v square by c square.
Right.
So if you put v is equal to c, that is your velocity, it will explode. So which
Yes.
doesn't make any sense.
Right.
So,
Right.
but in case of black hole, it may happen.
Right. Thanks so much, Somandu. I think it's a beautiful explanation.
I don't know
Thanks.
it's explained or not, but yeah, now I am no more physicist. I am a data scientist right now. So yeah.
Okay.
Amazing. Yeah, thanks, Anirban, for bringing this kind of questions. I mean, we get to
My
learn
pleasure.
a lot.
Shada. My pleasure.
And thanks, Amindu, for taking it up. Yeah. And next, I can see AIW raising hand. Can you please unmute yourself and ask? Yeah. Hi. You are on mute, sir.
Got it. Yeah, I just need to point out that I'm an absolute novice, but and I'm trying to get my head around a lot of the paradoxes that occur in quantum physics. But I think according to Feynman, then you can model many quantum mechanical events by the particles momentarily traveling faster than light and going into the past and reacting with themselves. And we're talking in quantum computing with quantum phenomena. So traveling faster than the speed of light is just part of the physics, as it were. And with, I gather, with quantum entanglement, then this entanglement of the states, the interaction takes part instantaneously, which seems to be something that many physicists are having difficulty getting their head round. Does that mean that the laws of relativity are broken? And I think there was much argument between Einstein and the quantum community about the reality of that.
Is it? That's good to know. So you are saying that Einstein's E equal to mc square can be broken down or can be contested using quantum computing.
He just didn't. He saw as the ideas of. He actually brought up quantum entanglement, I gather, to disprove some of the theories of quantum mechanics that Niels Bohr, I think, was postulating, and he lost the argument, but he didn't believe with spooky action at a distance. Trying to, I don't think that's the exact phrase, but the word spooky was involved in it.
Okay.
Yes, even I heard some news, I mean, few days back or few months back, someone did some publication on it, like where they tried to prove round is equal to MC square. I think if I can find the article, I will share within the chat.
Yeah,
Search for it.
I want to add one thing, Anirban. Yeah, this speed of light in vacuum, that's very important thing. Maybe in medium, you can cross the speed of light. Okay, when Einstein, I think as per I remember, postulate two laws. One was speed of light in vacuum is absolute constant, and laws of physics are same in all inertial frames. So this vacuum word is important. In vacuum, you cannot cross. So that was my point. Yeah, I forgot to
Okay,
mention.
but when you consider space, outside Earth, everything is space, free space. So it's a vacuum. So theoretically,
Theoretically,
like,
it's not vacuum. You cannot create absolute vacuum.
Okay.
Because
Right.
there is always
It might
some
have some
fluctuation is there.
Exactly.
Yeah.
Yeah. It's going back to the physics, and we have to recollect, what we actually read.
Yeah.
Thank you so much. Yeah.
Yeah. Thanks a lot, sir, for adding your insights for this questions of Anirban. I really appreciate. Yeah, we have a few more questions. We have one question from So Kino is asking, like, Kino has responded for no copy. Please do any possibility. Okay, so we have one question from HP. Do we have any possible de-encryption procedure for the elliptic curve kind of encryption via quantum means? Neha, do you know any such algorithm?
So for the quantum thing, I'm not very much sure, but if I talk about classical things, so yes, it provides.
HP, do you have any additional questions on top of it?
I was just wondering if it were possible, but yeah, not really.
Okay, thanks a lot. We have one more question from YouTube. Due to cloning theory, how can we use QRAM? Anyone, Neha or Viren sir?
So basically, QRAM, instead of your, I would say, classical bits, you have quantum bits. The rest of the components should remain the same in terms of using memory array or your input or output registers, which you use in the regular classical RAM. That's a very high level answer, so as to create a simile between classical and quantum computing and classical and quantum RAM. Essentially, conceptually, it'll remain that way only. And accordingly, that's how the whole expansion will come at the qubit level. Neha, feel free to add anything.
Yep.
I think, sir, you gave a very good answer. I also wanted to share same, but you shared.
Thank you.
So thanks, Viren sir. Any other questions we have from anyone?
Is it possible to broadcast with quantum computers? It feels like it's one-on-one communication and it's a fiber cable, right? But is it possible, like theoretically, broadcast from one device to many, given these quantum laws that prevent to repeat the same thread, right?
Yeah. Would you like to step in? I mean, this is also beyond my scope.
I didn't get actually questions.
Yeah, so he's asking about, like, is it possible to use quantum technology for broadcasting events? Correct me if I'm wrong, Marius.
Yes, that's exactly the question. Yeah, it feels like by the description, it's a communication between two devices through a physical media, like a fiber cable. So is it possible, with all the laws that you explained, is it possible to make it one to many, right? So one quantum device communicating to many quantum devices, not one to one.
So actually, research is going on it. So as of now, we were able to achieve it for a particular direction, a particular distance with a one-on-one. But I'm not sure about one to many. And but research is going on this. We are trying to, because we just have to put fiber optics everywhere, like where we want to communicate. So one-on-one it is achieved, but one to many, I don't think so it is achieved yet.
Thanks, Neha, for answering it. If you don't have any other questions, what I will do is I will share a few more things with you all, and about the community and how you can join us, and about the upcoming events. And I will briefly discuss about one of the use cases which I worked on and have already presented that last year in Christmas with the Alexandria Quantum Computing Group. But if any one of you are already working on making use of quantum in finance, then it might be like useful for you, or you might be interested in that. So just give me 10 more minutes of yours. I will share my screen. Let me know if you can see it. Okay. Is it visible to you all?
Yes, it is visible.
Yeah, slides, Neha, right?
Yeah.
Good. Thank you. So yeah, talking about this, right? So most of you would have already came across these kind of applications where we are trying to use quantum computers for portfolio optimization, option pricing, then stock price prediction by making use of quantum neural networks. Then also credit fraud detection, and many more applications are there if we jump to the real-time use cases of quantum in finance side. So similarly, like working for LSEC, London Stock Exchange Group, I was also exploring like how we can make use of quantum computers with real-time data, or with real data, rather than just making use of what has already been provided to us. So there are different quantum packages, right? Like Penny Lane, one by D-Wave, one by IBM, the Qiskit one, which I have used. And so portfolio optimization is just one of the optimization problems which can be solved on quantum computer. But beside that, there are many other optimization algorithms which companies are working on and trying to get it executed on the quantum computers. So in this, what I did was I tried plugging real data from, basically I used historical data only, but it was being used by Icon Data API, which is one of the product of LSEC. And I was trying to reuse the Qiskit implementation of portfolio optimization. So there I ran a few of the challenges which I want to talk about, so that if anyone else is trying such a sort of implementation, that can be useful for you guys. Okay, so in starting, I didn't talk about myself, right? So I'm Shadab, and I started my career back in 2017 as a data scientist. And recently I joined LSEC as a developer advocate last year in September. And my specialization is in data science, machine learning, and interest lies in quantum machine learning, in which I'm trying to explore the application of quantum finance and how QML can be used in healthcare. And so these are a few of the links. So talking about the challenge, right, I will exit the presentation here, and I will take you to the blog for where I have documented each of the steps. Okay. So in Qiskit Finance, you see, right, let me zoom it out. There are different sort of applications. There are two which I have mentioned here: portfolio optimization and option pricing, in which we use Monte Carlo simulation for option pricing, or quadratic programs can be used. So if you see the Qiskit implementation, right, and before jumping to that, portfolio optimization, if any one of you don't know what is that, then you all would have heard about the stock market, right, in which investors select a certain set of stocks in which they want to invest in. And in those list of stocks, few stocks can be highly volatile, which can be highly reward and highly risky. with high risk, and there are few stocks which are having low volatility. So the chances of profit will be also quite minimum, and even the risk will be minimized there. So using portfolio optimization technique, right, what the investor try to achieve is like they should select the list of stocks or options. Options means here I'm referring to stocks, okay, that it should give the maximum return to the user and with minimum risk. Okay, the portfolio should be diversified in such a way. So there are three basic terms which you should be aware of: risk, return, portfolio. Risk is deviation of the return on investment. Return is reward of investment, like whatever we are investing, how much profit we are going to make out of it. And portfolio is the collection of assets. It can be stocks, it can be currencies, it can be bonds, anything. Okay. So mean variance portfolio theory, or modern portfolio theory, was being used for the implementation of it. And if you go and see the Qiskit implementation, right, they are making use of few of the open source data providers like Yahoo Finance or Wikipedia, something like that they are using. But what if you have to plug in some data, custom data providers? In that way, how we can get our data ready so that we can directly plug into the Qiskit and play around it, right? So when I dig deep to the package of Qiskit, right, what I found that they have a class where they have implemented a class in which they are creating the data in such a format which is being input to the next step in the pipeline. Okay, so this is the code. I will come back to the icon later, but the base data provider class is the code where they have modified the data in a certain format, and they've created a few of the variables, right? So what I have done here is like, it's a very simple basic step. If you know Python program, you can easily implement by your own as well. So I inherited this class in my custom class, which I'm using for loading the data from the icon. So icon is the data provider here. And I created the same variables which they were creating in their package. And the same function I have created, so that when I call that function on the icon data provider class object, I should get the results exactly same as it is, so that I don't have to struggle much in figuring out why I'm getting this error or why my data is not being accepted by the quantum computer or quantum algorithm which I am using in the next step, right? So just this basic step helped me in fetching the data from icon in the required format, which can be easily plugged into the Qiskit, and we can reuse the Qiskit component itself in the next step. So here you can see that I'm just calling the icon data provider. It acts as the same as we are calling some other data provider in quantum finance library of Qiskit. And further, I can do the portfolio optimization algorithm run on quantum computer. So this is what my data look like, and this is the historical chart for all the 5 stocks of Facebook, Apple, Amazon, Netflix, and Google. And then simply like we calculate. So these methods and functions also, which you are seeing, that all these are pre-implemented in Qiskit, so that I can reuse that. I can just call these methods and functions as well on my class object, and I will get the data in the desired format, what is being expected from the package. Right, and few of the custom implementation also I did by my own outside the package, like plotting the correlation metrics and all. And so this is a pair plot to see the correlation between the stocks. And there were a few of the utility functions as well, to so that when we execute, right, it can print out the results, whatever we are looking for. So the comparison was between classical eigensolver and then the quantum implementation of it. We used QAOA and variational quantum eigensolver, and we compared the result. And this is of, let me see. Yeah, so this is the classical eigensolver, and since this is the classical implementation, right, you can see all the output were giving me the probability of a particular class, which stock should be picked in. And then I did PQE implementation, And obviously this was being just run on simulator, so we cannot expect the same result every time. And one more thing just to call out, the higher number of qubits you will keep, the more optimal results we will be getting by executing this on real quantum computers. Okay, so here you can see because of some noise or because of the probability of when we execute this using the quantum implementation, right? A new thing has been also, a new combination has also been introduced, but higher probability is of the same stock combination what we got from the classical eigensolver. And the same is with the QAOA implementation as well. So just I wanted to share with you all, right, if you're working on such use cases where you do struggle while plugging in your own data or real-time data with this kind of
Hey, Shadab,
packages. Yes.
I have a question. I know it's a beautiful example, and finance is a perfect field to leverage all the quantum and multiple factors and multiple variables.
Yes.
But I'm sure you have run this, and you did share about some correlation between the equities also.
Yes.
How much is the time period you are taking where these kind of, I would say, predictions in this term are meaningful and usable? And I'm taking specifically the introduction of geopolitical factors, because those, they flare up at the instant. No one expected that any war would last 2 months. No one expected that it'll go to this kind of gravity where it is now today, and it's getting stretched so far and impacting the global economies of the world. Right? So,
yes.
So from that angle, when you do this kind of, I would say, modeling, is there anything you have thought of or you plan to take into consideration that, okay, throwing this ranch could make this entire prediction totally different, or how it'll basically react to that? I know it's a very difficult question, very difficult. It's easy to ask the question than to answer, but I'll put you in the hot seat to make you think.
Yes, it's a really beautiful question, sir, and you're making me think in such a direction. So when I implemented this, right, so I was just looking, so my main motto was like, researchers are already working on proving the benefit of quantum computers, right? And they are publishing papers and everything, and companies like JP Morgan and Goldman Sachs, I think, Goldman Sachs I'm not sure of, but JP Morgan especially, they have their own quantum team developing the packages and publishing their work outside for the research community. But my main focus here was to demonstrate to the user how they can plug in the data from some real APIs existing outside and not panic with the complication of the quantum packages, rather than they can just easily inherit the functionalities of these packages and reuse without rewriting the whole code from the scratch or leaving it in the middle. But talking about the advantages, like what quantum can have in comparison to in seeing the trends which is changing very fast in the industry. I mean, there are different factors which plays a very crucial role, right, when we have to make these kind of prediction. Here, if you see, we have a very simple data. I have just considered closing price of each of the stocks. But when it comes to the real scenario, right, in that case, there are many other factors as well which are accountable in the prediction of how this particular stock is going to perform in the future. For example, if I talk about the company performance, the suppliers with whom they are buying any raw material, or the operating profit cost, right? These factors, then their ESG score, or the deals which they are making, or they are buying out the companies, and even the sentiment around that particular stock. And sentiment is something which changes very rapidly. We don't know, like, if a stock is performing very well today, it can crash tomorrow. The market is such unpredictable. Any event can occur, and that can be the cause of the downfall of that stock.
And that's why I was asking that term, the period which you are trying to take for these prediction is very important.
Yes.
And how short, how long can we go, and what are the factors which could really impact, especially if we take the example of last 15 days and how the market has behaved.
Yes.
Nothing
So
matters. Earnings, predictions, nothing matters, because
Yep.
you have seen the choppy market, ups and downs.
Yep. Yes.
Right. And within the same day, it's not that we are talking of days here.
Yes. Within the same day, we have seen
market
the
opens with like whatever numerics, and
it
now within
crashes.
3 hours it has gone up and down twice.
Yes. A few
God
of the
bless,
examples also
any
we have.
prediction, any modeling will come to a halt. But in the normal conditions, if we take out all those uncertainties, and again, we want and we love quantum for the fundamentals it has given around us, uncertainty and all those factors which we can incorporate. But at what stage can something still be to some shorter period be even incorporated? And I'll give the example of this company which is doing a wonderful work. They had presented on one of our forums, Chicago Computing. They came up with the modeling.
Yes.
You could provide your portfolio, and for paltry $50, they were able to essentially give you some prediction. And we were discussing at that time also, and today it is more meaningful in the current circumstances and this wartime which is going on in Ukraine and Russia. And although two countries are involved, but look at the geopolitical effect. The entire globe is involved. It's just like everywhere I can see everything is going topsy-turvy in terms of commodity prices and stock prices in turn. And companies come, they deliver good results in spite of all these things. Some may even be saying that they are not impacted by any Russia sanctions or anything of that sort, but yet the impact is there. And yet market is not ready to kind of not penalize them and give them the reward. Very few. But go ahead, you had something to say. And I believe Neha open the camera. She wants to say something as well.
Yeah. Also, like you all are able to see my screen, the Medium blog which I'm sharing, or my slide.
Yeah, we can.
Yes, we can.
Blog page, right? Because I can see the questions in the chat. Few people with questions.
Yeah, you are specifically talking of FANG, and FANG has been beaten in the last 5 days. Beaten to death.
And
not
FANG
to death,
is
I will
not
say to the kind of supremacy they held so far.
Yes, and FANG is not the right set of stock. Actually, if we talk about the real-time scenarios, right? Because they all have correlation with each other, and we don't pick such stocks which are highly correlated in real-time scenarios.
Right, and that's why we say diversified portfolio.
Yes. So, I mean, if you are performing something real-time, right, which, I mean, as you were telling about that, it needs to be meaningful, then there should be more number of stocks, and the system which is available for public and the algorithm which is publicly available, right? No one wants to make their secrets open out in the public, like especially in the finance. Whatever quantum algorithm we will be seeing, like which are meaningful and which can have impact in real-time scenario, those are lying with the companies which are providing services to the customers, or B2B or B2C, like whatever market scenario they are operating in. But I mean, and it will take some time to get this research publicly open till it is very common for everyone, right?
But coming back to what you said, I'm just interjecting here, sorry, because it's important.
Yes, yes. Sir.
When you say these stocks and the number of stocks, and someone mentioned just a few minutes ago that we do all these statistical computation, from that important angle, there's a very interesting angle in terms of number of stocks. Although I see in your model, you have taken FANG, but and then if we look for a diversified portfolio and the natural diversification, they say you can try with a sample of 30. That is a statistical number. And
30, 50, 100, like
30,
that.
whatever. And as you keep on increasing that number, you are basically reducing the uncertainty and the fluctuations. And if I go in the quantum terms, the simple harmonic motion around the mean, and that's where we try to peg at. But then, as you earlier mentioned, it's a risk and the reward, and the volatility, and highly volatile the stock is. more rewarding it could be sometimes, and more damaging it will be also sometimes, right?
Yes.
Because it moves in both the directions simultaneously around its mean, which we have different terminologies in the stock for it. 50 days moving average, 100 day, 200 days, or whatever we want to go around and after. But that 30 is a very interesting number, and I'm sure in some of your models you may want to plug in those and see how that piece has behaved, or you might have already done so, because that's a very renowned example of taking those many stocks to minimum with when you set up the portfolio and you go about that. And a lot of portfolio managers, I'm sure they follow different principles and different number, and they are into the business daily. And that's why I said some term, some number, something. How do we get to that magic thing? I don't know the answer, but I have the question.
Yes, even I'm not exactly sure, sir, but that's really interesting point to highlight and to think of.
Yeah. Thank you. And I want you to complete your thought. I didn't mean to stop your thought.
Yeah. So yeah, that's what I wanted to share with the community. So if they are like just starting with or want to try their hands on in the applications of quantum finance, right, they can refer to these kind of use cases. And if they're facing some error with plugging their own data or making their own use cases to try out these kind of applications in different areas, you can just go to the package level source code of the packages of the libraries, and you can see like what they are doing, and you can do some bit of modification, and you will be easily able to run these kind of codes. And this is just publicly available example, so it's not like recommended for real-time portfolio optimization or any such scenario, but it's just for the learning purpose.
And maybe it might be better suitable now, I would say, in the current situation for bonds.
Yeah.
Who knows? It may be, well, I'm saying bonds, and next week it'll be untrue for bonds as well. but I would say, no, this is very interesting topic, and especially going back to Neha's example for quantum and crypto. And I believe we have discussed in various forums now and various sessions, and it was happy to see that Neha, you also reached to that conclusion for hybrid. And of course, yes, our AI based modeling can be very easily incorporated to quantum. That's why I strongly believe quantum will not take 25 years to evolve. It'll take 5 years or less. And I think it's at that inflection point now. And with that, I'll stop and allow you guys to go further. I may have to drop off very soon. Thank you, guys.
Thanks a lot, sir, for adding up and sharing the insights with us. I mean,
it's just my pleasure. I'm a learner like you guys. You are at whatever stage, I'm at whatever stage, but we all are constant learners. And that's what keeps us alive.
I'm a learner, sir, still, so.
Thank you. May I have a question?
Yes, please.
It looks like you're using Qiskit and Icon is very helpful and will be nice to look at it closely. I'm to learn it. With your help, maybe I'll communicate. And the question that I have is,
sir.
do you have scenario generation module in the package, or are you considering it?
Scenario generation, I mean, can you elaborate, please?
Sorry?
Can you please elaborate the scenario generation?
Well, scenario generation is a technique evaluating the risk and also in pricing. It's quite common in finance. So it looks like from the discussion with Dr. Golata and everything that was said so far, to deal with the geopolitical uncertainty, you need, in the time series prediction, you may want to consider, if it's possible, to do a momentary scenario generation of every movement impact. Okay, for example, if the supply chain is being stumbled by geopolitical situation, this may have ripple effects
On
and
this chart.
create a whole myriad or spectrum of scenarios.
Yes. So those kind of events are not being considered in this example. So I mean, these are the features which we can club in before doing the portfolio optimization example, right? So we can just pull the data from the data providers and can use that as a feature input for these kind of problems. But in this example, I have not considered any other scenarios apart from just the closing price.
Yeah, I know about scenario generation. You can take in account even situations of very, very low probability. I'll give you extreme low probability. Suppose somebody is shooting Putin tomorrow. What effect, how the market will react?
Yeah.
This is a big question, maybe, hopefully
In
not so
classical,
theoretical.
yes, in classical implementations, we do consider these kind of scenarios. So this is the separate example. But if you go to let me take you to this. There are different examples. You can find articles, videos, and blogs on our community platform, where you can see real-time use case and applications, not the quantum one, but if it is just specific to the finance part. So if you're looking for such examples, right, where they are considering a scenario-based input, or they are considering sentiments or deals done by the companies, or any stoppage or excess in the supply, or any gap in the demand and supply, right? So there could be some examples which I can reshare with you where these kind of scenarios have been considered.
Yeah, this will be nice to see, like not so fast.
Yeah, I can. I mean, me and Helen are planning for next session specifically for quantum finance. So I would be happy to discuss and talk about these applications in detail. Right now, we are already about to approach the end time. So in that talk, maybe I can pick up some real example where I can explain any of the finance domain in detail. So that it is relevant for real-time scenarios as well. And from there, we can look at the quantum angle of it as well, and we can take it forward.
Someone has a question for Neha. Does basic computing techniques like shared memory be applicable to QRAM? This is a question for Neha about the QRAM.
I think sir has already given this
has
question.
been already answered.
These questions are covered actually.
Thank you.
And so that's it from my side. I have shared the link of blog and meetup and the community portal in the chat as well. And again, just to reiterate, there are more upcoming events by Washington Quantum Computing Meetup Group. So please feel free to join us on the meetup and do attend these events. And apart from that, if you are interested in joining Quantum Computing India, so this is one of the community which I co-founded back in 2019. And this is one of the largest quantum computing India community, quantum computing community in India. And we do host hackathons, workshops, fellowships, and live events as well. So it would be really appreciated if you want to join us. So you can go to this link, quantumcomputingindia.com. We have LinkedIn page and meetup group as well. You will get all the information from this website. Okay, and and talking about, okay, Achari has a question. Do we have to pay to read the article? No, Achari, you don't have to pay to read any of these articles. You can just register yourself and you can start reading the articles, watching videos, exploring the APIs and everything.
Shadab, yeah, your session is next week, or what time it is? I would be very interested to join.
It's not yet planned, so
okay.
I need to check with Helen. Yeah.
Okay, I hope it will not be at 6 a.m. my time, but if it is, it is.
This was too early for you, right, today?
Yes.
Yeah, we will
6
plan
a.m.
it
on my
accordingly.
Sunday. 6 a.m. on my Sunday, but I loved every minute of it. Guys, don't take me wrong. It was good. Thank you, though.
That's,
yeah.
Sorry for putting you in this kind of scenarios. Next time we will plan
as
it.
I'm saying, next time put your session at maybe little later time.
Please. Sure, sir. We will plan it.
I'm sure we'll have more attendance from Vesta also in that case.
Yes.
And more the merrier.
Yeah. Yeah. Achari Neha has a thank you, sir. Achari, Neha Acharya has a question for you. She's asking for the article, I think. Yusuf.
Yeah, hello.
Yes, please.
The article is not accessible. I have to buy it 41 euros. Is it normal or is it accessible somewhere? The emerging trends of quantum computing towards data security and key management. I mean, the correction is accessible, but not the original article. You are muted, Neha. I cannot hear.
Neha, you're on mute.
Yeah, I can share with you. This PDF I'll share with you. I'm writing my email here.
Okay. Okay, thank you very much, because I will request it from you. Thank you.
Okay, I'll share. I'm so sorry.
No problem.
I'll share.
Thanks, Yusuf and Neha. And thanks a lot, Galot, sir, for sharing your views. Neha, you want to add on something?
Yeah, so I'm open for the collaborations also. We can work together if anyone find my work or my knowledge suitable for anyone's work, or I'm happy to collaborate with who wants to collaborate.
Please feel free to reach out to Neha if you have any such ideas or if you want to collaborate with them.
Yeah, so I have wrote my email ID in the chat box, or for further questions or anything which I can help, please share with me. Thank you. And thank you so much for giving me this opportunity. I'm grateful. Thank you. Thank you so much to everyone.
Yeah, she's just sending her email ID publicly. Just a second. May I send it privately?
Okay. Let me just say.
Sure. And thanks a lot, Dave.
I did share my LinkedIn in case anyone wants to connect, please.
Thanks for sharing. Okay, thanks a lot for everyone for joining on such odd timings. And thank you, Viren sir, Dave sir, Helen, Neha. The session was really informative and insightful, and it was very interactive as well because of all the participants. And I hope to see this kind of interactive sessions more in future from Neha, Viren sir, Dave sir, and everyone. And if anyone of you are interested in speaking opportunities, right, or if you have something to share with the community, please feel free to reach out to us either through LinkedIn or through email. You're more than welcome, and we will see like how we can take it forward.
Okay, thank you, Neha and Shadev. So please share your slides with Helen and me. Okay, and we'll see you next time, maybe pretty soon.
Sure.
Yeah.
So I have shared my slide with Helen, and might be she is going to share further.
Okay.
Thank you.
Thanks, everyone. Have a good day.
Eid Mubarak, Eid Mubarak to all of you, to all of us.
Absolutely, Eid Mubarak.
Yeah,
Eid Mubarak to you all.
It's tomorrow.
In West, I think it is tomorrow. In India, it will be day after tomorrow.
Okay.
It's all on Chand, moon.
Yes. Okay. So guys, have a happy Eid. Enjoy with the family. And thanks for attending the event.
Same to you.
Bye.
Thank you. Bye.
Bye. Thanks, Neha. Bye.
Bye.